There are 8 primary ways to generate electrical current. Firstly, chemical action, exemplified by a battery. Batteries convert chemical energy into electrical energy through redox reactions. These reactions involve the transfer of electrons between different chemical species, creating a potential difference that drives the flow of current. Different types of batteries utilize various chemical reactions. For example, lead-acid batteries, commonly found in automobiles, use a reaction between lead dioxide, lead, and sulfuric acid. Lithium-ion batteries, prevalent in portable electronics, employ lithium compounds as electrodes. The voltage and current capacity of a battery depend on the specific chemical reactions and the design of the battery cells. Secondly, mechanical action, as seen in a generator. Generators convert mechanical energy into electrical energy through the principle of electromagnetic induction. A conductor, typically a coil of wire, is moved through a magnetic field, inducing a voltage across the conductor. This voltage drives the flow of current. The mechanical energy can be supplied by various sources such as steam turbines, gas turbines, water turbines, or internal combustion engines. The output voltage and current of a generator depend on factors like the strength of the magnetic field, the speed of rotation, and the number of turns in the coil. Thirdly, thermal action, illustrated by a thermocouple. Thermocouples generate a voltage based on the Seebeck effect, which states that a temperature difference between two dissimilar electrical conductors or semiconductors creates a voltage difference between them. This voltage difference is typically small, but it can be amplified and used to measure temperature or generate a small amount of electrical power. Thermocouples are commonly used in temperature sensors and industrial control systems. The voltage generated by a thermocouple is proportional to the temperature difference between the junctions, and different types of thermocouples have different sensitivities and temperature ranges. Fourthly, photovoltaic action, demonstrated by a solar cell. Solar cells convert light energy directly into electrical energy through the photovoltaic effect. When photons of light strike a semiconductor material, such as silicon, they can excite electrons, freeing them from their atomic bonds. These free electrons can then flow through an electrical circuit, generating current. Solar cells are typically arranged in modules to increase the output voltage and current. The efficiency of a solar cell depends on factors such as the material used, the wavelength of light, and the temperature. Fifthly, piezoelectric action, where a crystal generates current when mechanically stressed. Piezoelectric materials generate an electrical charge when subjected to mechanical stress, such as pressure or vibration. This phenomenon is known as the piezoelectric effect. Conversely, when an electrical field is applied to a piezoelectric material, it undergoes mechanical deformation. Piezoelectric materials are used in a variety of applications, including sensors, actuators, and energy harvesting devices. The amount of charge generated by a piezoelectric material is proportional to the applied stress. Sixthly, electrostatic action, as in a Van de Graaff generator. A Van de Graaff generator uses a moving belt to accumulate electrostatic charge on a hollow metal sphere. This charge creates a high voltage on the sphere, which can be used to generate sparks or power other devices. Van de Graaff generators are commonly used in physics demonstrations and research. The voltage that can be achieved by a Van de Graaff generator depends on factors such as the size of the sphere, the speed of the belt, and the humidity of the air. Seventhly, electromagnetic induction, as seen in a transformer. A transformer transfers electrical energy from one circuit to another through electromagnetic induction. It consists of 2 or more coils of wire wound around a common core. When an alternating current flows through one coil, it creates a changing magnetic field, which induces a voltage in the other coil. Transformers are used to step up or step down voltages in electrical power systems. The ratio of the voltages in the 2 coils is proportional to the ratio of the number of turns in the coils. Finally, magnetohydrodynamics, which involves the movement of a plasma through a magnetic field. Magnetohydrodynamics, MHD, generates electricity by moving a conductive fluid, typically a plasma, through a magnetic field. This movement induces a voltage in the fluid, which can be extracted using electrodes. MHD generators are highly efficient and can operate at high temperatures, but they are complex and expensive to build. MHD generators have potential applications in power generation and propulsion systems. The voltage generated by an MHD generator depends on factors such as the strength of the magnetic field, the speed of the fluid, and the conductivity of the fluid. These 8 methods represent the fundamental ways to generate electrical current, each with its own unique principles and applications. The choice of method depends on factors such as the desired voltage and current, the available energy source, and the cost and complexity of the system.